Okay, so this is the first part for the lecture for November 7th. We are talking about the K function. And so this is kind of where we left off. We developed the K function, and we said that the K function is the expected number of points. Well, actually, the K function calculates the average number of points within a radius d of any other given point. And so it's a function. D increases, the radius gets larger and larger and larger. The average number of points is going to grow. And under complete spatial randomness, the K function should behave like pi d squared. So to make things easier on our eyes, we do a transformation of the K function to create the L function, and then under complete spatial randomness, the L function should approximately follow the 45-degree line. So we jumped to R. And we ran some K functions of various processes. We did it for the oh, sorry. Okay, now I've got my library loaded. Let me try this again. So here's a Strauss process with gamma equals 0.2. We could draw the K function. I'm going to focus on the L function. What we see is that the L function, sorry, I'm not plotting the L function yet. Here's the L function. What we see is that the L function is showing too few points. If the process followed complete spatial randomness, we would think that the number of points as a function here of R would follow the 45-degree line. At short distances, we see the Strauss, the L function for this Strauss process is saying there are too few points, and that's because of the regular behavior of the Strauss process. What we also see is that up here, the K function or the L function is going to correct itself over time. As you look at correct may be the wrong verb here, but as we look at larger and larger and larger radiuses, we're averaging over a larger and larger area, and the L function has to estimate lambda, the intensity, and so it just takes the total number of points, divides it by area. As we look over a larger and larger radius, that average is going to approach that empirical average of number of points divided by area. And so as radius gets larger and larger and larger, we're necessarily going to see the L function approximate the 45-degree line, regardless of the process. So what the L function does is it tells us kind of at what distances we're seeing deviation from complete spatial randomness. Neyman-Scott's going to have the opposite behavior. Here is a realization of a process with clustered behavior. Here is the L function, and so the average number of points seen at these short radiuses of like 0.05 is greater than we would expect under complete spatial randomness. Okay, so what we're going to do next is we're going to use these L functions to estimate parameters of the underlying processes, the Strauss process or the Neyman-Scott process. Okay, so first we're going to do the Strauss process. Now, in both of those, what we saw was kind of by eye, we can get the radius of most interest. At what radius does our observed L function deviate greatest from complete spatial randomness? So we're basically looking for the radius at which that vertical height is greatest. And then that's going to be our radius of interest. But what we can also, and so that would be what we would suspect in a Strauss process, that would be the radius of the disk that inhibits further points from being located near existing points. What we can also do is we can estimate the C, or that I believe it's gamma in the STAT library. It's that probability of accepting a point within that radius inside the disk, as written here. So how we can estimate C, if C is the probability of accepting a point inside the disk, C hat would be the average number of points within the disk of radius d divided by the expected number of points from homogeneous Poisson process with intensity lambda. So if we take what we observe and divide by what we'd expect, we assuming that we have regular behavior, this is going to be a number less than 1. And what we'd like to do is get this from our k function. Well, this numerator basically comes directly from our k function. The k function, when multiplied by lambda, what we saw in the notes was that k times lambda gave the average number of points within a disk of radius d, and the expected number of points for homogeneous Poisson process would be intensity times the area, and the area, of course, of a disk with radius d is going to be pi d squared. So we could get C hat directly from the K function. To get the L, to do it with the L function, what we're going to do is we're going to replace this K hat with L hat using our conversion from before. The pi is taken out in our jump from K to L. And so pi times L squared equals K. So we can replace this with pi times L squared, the pi's cancel, and our estimate for C is going to be the value of our L function at our radius of distance squared divided by d squared, which comes from here. That will be, so basically it's just the slope of our line, that you can think of this as rise and this as run. If I take the slope and square it, that should be our estimate for D. So let me return to R and we can see it. Let's see here. Okay, so here in line 283, I'm going to estimate the C, or gamma, C in the notes, gamma in STAT library of our Strauss process. I'm going to generate a Strauss process with the parameter of interest, that C or gamma is 0.3. And so here is the realization of the Strauss process. Now I know, because the radius of addition is 0.02, but if I just collected data, I would only have this to work with. And so what I would do is I would look at this plot and I would ask, where is the maximum distance, the maximum vertical distance occurring? And it's not abundantly clear. You might pick 0.02, you might pick 0.03. I'm going to pick 0.03. I haven't shown this, but this curve is going to slowly wander back to the line because of the reasons that we talked about before. So what I tried to do was I tried to find basically kind of this, maybe it's this point right here. And so I located that guy. I said it's at 0.036, 0.019, and that was of course done by trial and error, but basically here is the location of the point on my L curve. So the slope, the rise would be 0.019, the run would be 0.036. My estimate for C would be the square of that value. And when I get C hat, I get 0.278. And notice that it is pretty good. It's pretty close to the true value, which was used to generate this data of 0.3. Now, I totally rigged it. I did a few Strauss processes to get a nice picture and to get a nice estimate, but what we hopefully can see from the notes is that with our understanding of K function giving sort of normalized number of points, average number of points found within distance R, we can work from that and from that definition of K function. Here, and work forward to get an estimate for C. Okay. Let's do the same thing for the Neyman-Scott process. So again, what we're looking for is kind of that maximum distance, that radius where the maximum deviation from complete spatial randomness occurs. We're going to use this point and somehow we're going to estimate a quantity of interest for the Neyman-Scott process. And the quantity of interest is going to be the average number of events per cluster. So recall Neyman-Scott or Poisson cluster process, you start with a parent, it generates some offspring. What we're trying to do is we're trying to find the average number of offspring. That might be a meaningful quantity for our process of interest. And so it would seem like that would be attainable because this L or this L function is giving us something about how many events we're seeing within a radius R. And so if that of course is going to be greater than what we would expect under complete spatial randomness. So this value should have some information about that number of offspring. So let's see if we can figure out what that would be. So you start off by finding R hat. We know that lambda times K is the, I really don't want to say, well, expected, I guess, is okay. Average number of points within distance R of any point. That's in our observed process. So that's not related to complete spatial randomness. This is what we are observing in our process. We have to plug in a value for lambda, which is the overall intensity. So the overall intensity is just number of points observed in the region. Remember, we know that because we start with a map data set. We start with knowledge of all the points. Divide that by R, that would be a natural estimator of intensity. So this quantity in itself should give us kind of what we're after, that expected number of points. What I'm going to do again is I'm going to replace this K with something in terms of L. K hat is equal to pi times L squared. And so this quantity here, pi times L squared times our average intensity, is going to give us an estimator of the number of points within a distance R. So if we identify that distance of maximum deviation, this will give us the average number of points. So again, let's jump to R and see this. Okay, so I'm going to generate a Neyman-Scott process. Notice what I'm doing is rather than having a random number of offspring, I'm going to have exactly 5 offspring for each one. But if we could replace that with a number that's Poisson generated with mean 5 or something like that. Here is our clustered process. Here is our L function. Again, we see things increase, and then this L function again is going to slowly come back to what would be expected under complete spatial randomness for larger and larger values. Because the radius was 0.05, we know the true maximum deviation, that true radius of interest would be 0.05, but working only from this L function, that wouldn't be apparent. I think that maximum radius is occurring about here. Again, I find that point kind of by trial and error. It's about at 0.075, and this height is about 0.15. So the so my L is 0.15. My number of points is 77. And this was generated on just a unit square here. So I guess I don't actually do the calculation here, but I think it's back in the notes. So n over d is 77 over 1. I have pi, I have 0.15 squared. I put that into my calculator and I get 5.44. And so again, we see that this does return something that sounds like what it should be returning. What we started off asking was get an average number of events per cluster. And we know from the way we generated it, that number was 5. We're getting an estimate of 5.44. Okay, so what have we done? We have spoken a little bit more about the L function. We have used that L function, and the K function is what's interpretable. The L function is what is easy to be read from a graph. But we use the interpretation of the K function to get reasonable estimators. Certainly they're a bit ad hoc feeling, but they're kind of like doing our variogram estimates by eye. We get some parameter estimates which are useful for describing either the inhibition we see in, say, a Strauss-like, and something that we could presume comes from a Strauss process, or the average number of offspring that we'd see in a Neyman-Scott process. So I'm going to stop this recording here, just because it's easier to post shorter videos. I will follow up with part 2 shortly.